This is lecture 16, where we will be looking at the error analysis for solutions of ODE as well as improved methods. Now, when you recall Richardson's extrapolation from our lectures on numerical integration, we know that we can combine two solutions of lower order accuracy to obtain a solution with higher order accuracy. So for example, you can combine two trapezoidal rules to get a solution that has the same order of accuracy as your Simpson's 1/3. Since solutions of ODE are essentially the same as performing an integral, we can also apply the same concept that we have with ODE solvers with the Richardson's extrapolation. So if you recall, the RK4 method that we have considered has a local error of order h to the power 5. So if we set y at t plus h to be the solution that we obtain using RK4, at the next time step, or the next step where h is the step size that we have, then we can basically write our yt plus h as the solution that we get from our RK4 using step size of h. And because the leading error term is order h5, similar to what we did for numerical integration, we can write this as ah to the power 5, bh to the power 6, and so on. So the leading error term would be order h to the power 5, and we will call this equation 1. Now suppose that we halve the step size. Okay, so instead of solving it with step size of h, let's say we solve it with step size of h over 2. So when you solve it with step size of h over 2, in order for you to get y at t plus h, it means that you will have to perform your RK4 method 2 times in order to go from point t to point t plus h. So using step size of h over 2, the solution at t plus h can be written as 2 times h over 2. So the 2 times is basically, as I said earlier, the reason we need that is because we need to repeat the RK4 method 2 times in order for us to reach the time that we want. So on the right hand side, you have RK4 solution that we get from applying the RK4 method 2 times, and here you have 2a times h over 2. Then you have, similarly, you have 2b of h over 2 to the power 6, and so on. So this is equation 2. Now the reason the coefficients 2 is present here is again because we are applying the RK4 method 2 times. We just introduce a coefficient 2 here to account for the fact that the RK4 method has been performed twice. So the idea right now in terms of using Richardson's extrapolation is to combine equation 1 and equation 2 so that the leading error term gets cancelled off. So in our case here, the leading error term is order h to the power 5. So can we combine equation 1 and equation 2 such that we are able to then obtain a solution that has a higher order accuracy? Okay, so one way to do that is to take equation 2 and to multiply it with we'll take equation 2 and we'll minus off 1 over 16 of equation 1. So we're going to take this equation 2 here, we're going to minus off equation 1 that is multiplied by the factor of 1 over 16. So in doing so, on the left hand side, we get y at t plus h minus y 1 over 16 at t plus h. So on the left hand side here, I've just written this as y at t plus h because that is the solution that we want. The solution of y after being the solution of y that we get after we applied the step size of h from the time point of t. So on the left hand side we have this. On the right hand side we are going to get the RK4 solution that we obtain using step size of h over 2 minus 1 over 16, the RK4 solution obtained with step size of h. And so in doing this, the leading error term here will get cancelled off because you will then have 2a h to the power 5 over 32 minus a h to the power 5 over 16. Okay, so this entire term, or your h to the power 5 term, now reduces to 0. So your leading error term now becomes h to the power 6. So if you express that out, you get bh to the power 6 1 over 32 minus 1 over 16, and of course your next term would have been your order h7. So I'm just going to write it as this. Alright, so what we want essentially is we want the solution at y at t plus h. So if you write this becomes 15 over 16 of y at t plus h is equals to the RK4 solution obtained with step size of h over 2 minus 1 over 16 of the RK4 solution with step size of h. And because the leading error term now is order h6, I'll just write this as order h6. Alright, and finally if you rewrite this, you get 16 over 15 of your RK4 solution obtained with step size of h minus 2 h over 2 minus 1 over 15 of RK4 at step size h. So this now has a leading error of h to the power 6. So if you look at this here, what we are doing is we are using Richardson's extrapolation to combine two solutions of RK4 to get a solution that is one order more accurate than your RK4 solution. So does this mean that we can actually apply Richardson's extrapolation every time to our solutions of ODE? As we have shown in the mathematics or the derivation that we have done, in order for you to perform your Richardson's extrapolation on your RK4 solution, you need to halve the time step or the step size every time. So every time you halve the step size from h to h over 2, you double the number of times you need to perform your calculation. So for example, let me draw it here. If you're at time 0 and you're asked to solve until 10 seconds using h of 0.1. So using h of 0.1, it means that you need to perform your RK4 100 times to go from 0 all the way to 10. If you're going to use RK4, you're going to use half the step size of this, which would have been 0.05. So using step size of 0.05, you would need 200 steps now to actually get your all your solutions from 0 to 10 seconds. So this becomes a limitation because the number of steps that you need to perform for your RK4 doubles whenever you halve the step size. So as the step size gets smaller and smaller, the number of steps that you need to perform becomes higher and higher. So the algorithm basically becomes inefficient. Now in reality, whenever we solve an ODE, the error regions with high error does not occur everywhere within your solution domain. So most of the time, the error usually occurs at certain points, and those certain points happen when the solution has an abrupt change in the gradient. So an example that I can give is actually this. So the red dots are basically the points of time over here, and the variation of the function is given by the blue curve. So you can see in this region over here, the gradient of the solution y changes abruptly, meaning that the gradient here is positive, it goes to 0, it suddenly gives you a sharp negative gradient before it goes to 0 again, and then it goes up. So if you are to accurately solve this ODE, the step size that you need to capture this region here needs to be small enough. However, if you set your step size to very, very small to capture this region, but the rest of the region does not require such a step size, then it becomes very inefficient with regards to your numerical code that you will find. So our question now is, are we able to find where in the region where this gradient changes very high so that we can apply a smaller step size in this region over here and larger step size in this region? So that is the question that we want to try to solve in this particular lecture. We don't want to use a small step size for the entire solution domain, because if your step size is very small, yes, you will get the accuracy, but your code may take a very long time to solve just because it needs to break down everything into very, very finite segments over here. While that is important in this region, it may not be important in this region or in this region over here. So how can we actually locate where the region of high gradient changes occur, and can we prescribe an ideal or an optimum value of step size for this particular region.